Hello?
Recording in progress.
Hello.
Hi.
We'll just wait for Reynolds to. Hello, hello. Okay, we'll just wait, see if Michaela joins, and then we'll get started. Okay, I think we'll get started now. So, just to start, so today we're going to be going through trigonomic functions. We did have the HSC mock exam to review logs for today, but I don't know if many of you got a chance to do it, so we're going to be doing it in next week's lesson. Yeah, that's basically all the housekeeping, so we'll just run into the lesson. Okay. Okay, so basically for today, our objectives is just going to be trigonomic functions. But it's going to be covering basically everything in trig functions. And then we'll have 30 minutes Q&A at the end, as per usual. Yeah. With trig functions, we're basically going to cover everything from trigonomic equations to graphing to inverse trig, differentiation, and also integration. So just starting off with some intro theory. So as you all should hopefully know by now, your sine and cosine functions will lie between -1 and 1. Yeah, these are pretty straightforward, but often forgotten. So just keep these in mind when you do questions, and you'll see cases where you're going to need to use these. But these are your basic properties. And then in terms of your differentiations, Can anyone tell me what actually, can I get Jonah? Can you tell me what the diff of sine theta is? Jonah?
Is it just arc sine? Oh no, well, it's a cos theta.
Yep. What about the diff of cos theta?
Negative sine theta.
Yep. And what about tan theta?
Sec squared theta.
Yep. Okay. And what about integrals? What's the integral of sine theta going to be?
Sorry,
The integral of sine theta.
negative cos theta.
Yep. So important thing to remember, sine integrates negatively. And following on, cos integrates positively. So it's basically a flip of what happens with the differentiation. And then you're also going to get this as tan theta. Pretty simple, it's just the opposite of the integrations. There is more complicated trig integrations, but those ones will be basically asked as questions, or there's also inverse trig, but we'll get into inverse trig later on. So we'll start out with questions now. Yeah. So I'm gonna get Sadak. Can you help me out with this question?
Do we have to, oh, we just have to put the part inside of the brackets on our calculator to get the exact value?
You can check, but you'll see that it's not going to give you a nice number if you do the sine inverse. You're going to get an irrational number. So if you do that way, you're not going to get an exact value.
I'm not sure what to do.
Okay, so first things first is we want to decompose what's inside of this cos. So the sine inverse 3 on 4. And one way we can do that is, you know that sine is going to be your opposite over hypotenuse. So, and therefore following from that, 3 is going to be opposite, your hypotenuse is going to be 4. So if you were to construct a triangle, if it were to let me draw, okay, and pick an arbitrary angle, say this one, and we'll just call it alpha for now, then this side is going to be 3, this side is going to be 4. What's this side going to be over here, the bottom side?
4 squared minus 3 squared.
Which is going to be?
Root 7.
Yep. So just one thing, just to write, let alpha equal sine inverse 3 on 4, because that's what I've done here. Okay, now from here, what do we know about sine inverse as a function? What does sine inverse lie between? What's its upper value and lower value?
Is it pi and negative pi?
Close. It's pi on 2 and negative pi on 2. So it just from the graph. So the graph will look something like from memory like this. Yeah. So we know where it lies between. So which quadrants is this where the sine inverse lies between?
The first and second.
Is this the second?
Oh, first and third.
It'd be first and fourth. So the minus pi on 2 is going to be from here going 90 degrees. So it'd be anywhere in here.
Okay.
So it's going to be your, if you remember all stations to central, it's going to be either this one or this one. The reason we're doing that is because we're going to apply a cos, so we need to know which values to take. Okay, so now that we know this, and we know that it's in these two quadrants here, that means cos x, what do we know about cos x given the two quadrants?
That cos is positive.
Yes, so we know that cos x will be greater than 0. So, from this triangle, what is cos x now?
√7 on 4.
Yep. Exactly. And this works because we've shown that cos x is positive given the domain of sine inverse x, or rather the range of sine inverse x. Okay, cool. On to a 3D trig problem. So Zoe, I'm going to get you to work on this one. You can take like 30 seconds to think before I ask you. Okay, any ideas so far?
I'm not sure. I'm just thinking because
Yep.
they haven't given you any lengths, so
Yep.
and it's a right angle triangle, so it's not like you just like cosine sine rule. Mm.
Yep, good observations. You
You
mentioned
can work out all of the angles for the other triangles, but I don't know why that would help you.
one thing you mentioned will be helpful, where you said that all of these are right angle triangles. You can use that somehow. Just think about how you might use that.
Oh, do we find the side length?
Yep.
Using that? Okay. Okay. Then so. Oh, right, there's a H. Did not see the H. Okay. So then sine 25 equals H over TC.
H
Or should we
over
use
TC, yes. True, but think about the objective of what we're trying to find. We're
Yeah.
trying to look at
maybe tan instead?
this triangle. Yep. Okay, I agree with tan.
And
So,
then CH.
pardon? BH?
Tan 25 is H over CH.
Yep. Tan 25 equals H over CH.
And then
This is from
tan 32 is
Mhm.
equal to H over AH.
Yep.
And then
So you've got two of the side lengths, which is
We
good.
can
Mhm.
we can use that to find the angle, but it would be in terms of h and the other side length.
So, right. Let's analyze the bottom triangle first. So this triangle here. If I was to draw this out and just like rotate it, it's going to look like this. So H, this is a right angle, this is A, and this is C. Okay. And we have an expression for CH over here if we rearrange this equation. We have an expression for AH if we rearrange this equation. And the angle we want is HCA. So, given that we can get an expression for AH and an expression for CH, how are we going to find this angle? Let's just call it X. Treating it
we
just like a normal triangle.
we can just use tan again.
Yep, exactly. So, if we use tan here, so we'll just denote it as angle HCA. Which,
I see.
what's
And then it
my ratio?
becomes tan, so the tan x equals tan 25 over tan 32.
Yes. So, you're correct. I'm just going to write out the full working. So, from over here, you can write HC equals H on tan 25, and AH equals H over tan 32. This is just rearranging these two equations here. And then from that, if we plug these over here, we're going to get H over tan 32 over H on tan 25. H's cancel, and then you should get a tan 25 on tan 32, because this is double divided, so it goes to the top. Okay, and so what did you get tan HCA to be?
Tan 25 over tan 32?
Yep.
Oh, you mean a simplified?
Actually, I wouldn't simplify it yet, because then it'll be less precise. So now what do you get for angle HCA?
36 degrees 44 minutes.
Yeah, correct. Yep, and this gives 36 degrees, 44 minutes. Very good. Okay. Now, part B, we want to find angle HBC to the nearest minute. So in here, we're looking for this angle right here. So I'll give you 30 seconds to have to think of how you're going to approach it.
I think I would use sine rule. So
Yep.
first I'd find BH using triangle TBH. Yeah.
Yep.
So BH is tan 30 is H over BH. So BH is H tan 30. And then we know CH is H over 10. 25.
CH. Yep. So HC equals, one second, it's not right. HC equals H over tan 25.
Yeah. And then we do, so BH divided by sine 36 44
Yep.
is equal to CH over sine angle HBC.
Yep.
And then we just solve.
Yeah.
So can take the tan down for both.
Mhm.
And then the H's will cancel out.
Yep.
And then it means sine HBC is equal to sine 3644 times tan 30 divided by tan 25.
Exactly, yes. And then and that's going to be okay. And what do you then get as angle HBC?
47 degrees, 47 minutes.
Is that the only possible answer?
No, because of the sign ambiguity.
So what's the other possible answer here?
180 minus that.
Yep. Yep.
So 132.
Yep.
132 degrees and 13 minutes.
Yep. Okay, so we know this. Now, could it be anything in the third or fourth quadrant?
No,
Yep. Why not?
because that would be negative.
Yep. Yes, it would be. So now between these two angles, are both angles correct?
Well, we can check
Mm-hmm.
that 47 plus 36. That leaves some room for a third angle, but they both leave room for a third angle. So I think so.
Okay, let's wait. Let me have a look. So that's okay. So let's take the case where you have the 47 degrees, 47 minutes, right? So if this is the case, you're going to have 47 degrees, 47 minutes as one of your angles, and then the other one is 36 degrees, 44 minutes. So if you sum these up, let's see what we get. 37, 6, 44, 44. You're going to get 84 degrees, 31 minutes. Actually, yeah. So your remaining angle sum will be 180 minus that, i.e. the size of your last angle. And that's going to give you 95 degrees, 29 minutes. On the other hand, what happens if we take 132 and 13 degrees?
We have 35 degrees left. Oh wait, sorry, 36. Wait a minute. Let me do that again.
Yep.
12 degrees left.
Yep. So we also do it. So that's going to give you, 168 degrees, 57 minutes, which gives you glance, which is going to give you 11 degrees and 3 minutes. So between these two, looking at the triangle back over here, do both make sense?
No,
Okay, which one doesn't make sense?
the 95.
Why doesn't it make sense?
Because angle AHC is already 90, so
Yeah.
angle BHC can't be 95.
Yes, exactly. So the only correct answer in that case is going to be 132 degrees and 13 minutes. Okay, so yeah, that's the trick there. They are trying to basically fool you on the sign ambiguity. Okay, very good. Yeah. The next one's going to be more of a trig equation type question. I'll get Shruti to work with me on this one. Yeah, I'll give you again 30 seconds to have a quick read through. Yeah, Shruti, any ideas?
Maybe you'd use the sine squared x, the identity 1 minus cos squared.
Yep, sure. Why would we do that?
So then you can expand and get it to like equal 0.
But can't you get to equal 0 regardless of that by just doing this? So
But the cos and the sine, like
yeah,
make them
exactly.
all cos.
Yeah. So yeah, that's the point I was looking for. You want to make it all one variable. Reason being, later on, you can basically do a u sub and say that u equals like cos x. But yeah, the point is you want it to all be one variable. So doing that, you're going to get, like you said, the cos squared, 5 cos x plus 4. Okay. And I'll just put everything to this side. X plus 2. Okay. What are we going to do from here?
So it'd be 2 cos x plus 1 bracket and then cos x plus 2, I think that goes.
Yep. What I would recommend, just as like when you have cases like this, to make it less like cancerous for your brain, just let u equal cos x, because this is very similar to a quadratic. In fact, it is a quadratic. So why not just make it look like a quadratic?
Yeah.
And then doing that, you're going to get 2u squared plus 5u plus 2 equals 0. And then, yeah, it's just cross method. So 2, 1, 2, 1, like so. So 2u plus 1, u plus 2 equals 0. And you get u equals negative a half, u equals
Negative 2.
negative 2. Yep, and then you can bring back in your cos x, like so. Okay. Now, from here, can do both of these work?
Oh, you'd cross out the minus 2 because it's cos x is between minus 1 and 1.
Yeah, perfect. So from the start of the lesson, we went through how this is the range of the cos and sine functions. So yeah, this can't be. So we're only looking at this. So based off this, which quadrants are we looking at? For our answer for x.
The second
Just the second?
and the third.
Okay, we are looking at the second and the third. So how are we going to solve for that?
So it'd be pi plus I mean, wait, I forgot how to do this.
So, okay, I'll just run through it for the first one, and then you tell me the second one.
Yeah.
So for the second quadrant, so the sine quadrant, essentially what you do is you treat this as if it's cos x equals a half, so as if it's the first quadrant, and you do your normal cos inverse, and tell me what you get from that. Just plug it into a calculator.
Pi on 3.
Yep, pi on 3. And then, so this is your first quadrant answer. And then to adjust it for the second quadrant, you do the pi minus pi on 3. So pi minus your first quadrant answer, which will give you 2 pi on 3. Okay, now how about the third quadrant answer?
You do pi plus pi on 2. I mean pi on 3.
Yep. So what's that going to give you?
4 pi on 3.
Okay. So are these our two answers?
Yeah.
Okay. Very close, but you fell for the trick. Let's scroll back off here. What is our domain for x?
Minus pi to pi.
Yeah.
So just be 2 pi on 3.
So this close, but not really, because think about what negative pi to pi denotes. All of this is pi, right? But also keep in mind, all of this is just negative pi. It's just what negative pi means is just instead of looking anti-clockwise, you just go from the clockwise direction. So negative pi to pi actually does mean the whole circle. So this 4 pi on 3 is still correct, but you just have to look at it from a negative angle. So basically, what we have over here for 4 pi on 3 is you're just adding a pi on 3 here, right? Like in terms of a diagram.
Mhm.
So instead of thinking about it in like this way, think about it as how far do we have to go the other way? So the other way, it's going to be pi plus 2 pi on 3, I believe. Actually, no, I'm tripping. So it'd be pi, and then that should be 1. Actually, no, yeah, that should be right. Yep. Wait, hold on. Oh, wait, that's why. Pi on 2, and then that is going to be. Yeah, so think about it like this. So going this way, you're going 60. And thus to go the other way, you need to go 120 degrees, just doing like 180 minus
Mhm.
60. And then 120 degrees divided by 180 gives you 2 pi and 3 radians.
Okay.
Oh, and then because we're going left, you add the negative.
Okay.
So technically it's like a negative 120.
Yeah.
So your actual second answer should be minus 2 pi and 3.
Okay.
Yeah, just be very careful of domains. They will purposely throw in tricks like using that negative. Even though it means the same thing, because it's not in the domain they've specified, they will dock a mark for it. Okay, some more trig polynomials for this next one. And for this one, Jonah, I'll get you to help me out. Yeah, again, I'll give you like 30 seconds. Okay, so for this question, we're trying to relate cos 3 theta to base cos thetas. Vagina, what is your thought process so far?
Um, do you use the cos squared theta rule, like cos A cos B rule?
As in like cos A plus B or
No, like what like cos A cos B equals 1 or 2, cos A minus B plus.
yeah. No, you do not. So I'll ask you this question. Do you think it's easier to solve from the left-hand side and make that into the right-hand side, or to solve from the right-hand side and make that look like the left side?
Oh, that's a 3 theta. Oh,
Yeah.
I was not looking at that right.
All good.
I thought it was a 30. It looks like a 30.
Yeah. So do you think it'll be easier to go from like proving the left side
Yeah,
equals the
yeah,
right? Okay.
yeah.
So how are we gonna go about doing that?
So split it into cos. I do like cos theta
Uh-huh.
plus 2 theta maybe,
Yep. Good.
and then that equals cos theta cos 2 theta
Yep.
minus sine theta sine 2 theta,
Good.
and then
What to do from here? So think about what you have in this expression that
and
you
then
could.
you have the two. You can like do it again.
Yep.
So cos. So it becomes cos theta brackets cos uh cos squared theta
Yep.
minus sine squared theta,
Good.
and then minus sine theta brackets uh sine theta cos theta.
Is it just one sine theta cos theta?
Oh no, two sine theta cos theta.
Good. Okay, yep.
And so then that becomes cos cubed theta minus sine squared theta cos theta
Theta cos theta. Yep.
minus 2 sine squared theta uh cos theta,
Yep.
and then just canceling the terms, so that's cos cubed theta minus 3 sine squared theta cos theta.
Mm-hmm.
Then we're trying to get okay, so then you use uh
So we want everything in terms of cosines. What can we
yeah,
convert to a cosine in this line?
the sine squared.
Yep.
So cos cubed theta minus 3 onto cos.
Are you using
Wait,
the double angle? Instead
yeah,
of
no, yeah, yeah.
think about
The
what
the sine squared equals 1 or 2, 1 minus 2.
think about what sine squared plus cosine squared equals. So what I'm asking you
Oh,
is
is it just 1? Sorry, is it 1? Wait,
yep, they do sum to 1. So
yeah,
then
yeah.
how can you re-express sine squared theta then, given that?
Uh,
So given this.
you can make it 1 minus cos squared theta, or 1 plus cos squared No,
minus.
minus, yeah.
Yep. Okay, yeah. And now? Now we expand.
Yeah.
What are we going to get from our expansion?
Cos cubed theta minus 3 plus cos cubed theta.
Yep.
3 cos cubed theta, so that's 4 cos cubed theta minus 3 wait,
Yeah, no, you're on the right track.
where's the cos theta from?
Wait, let me just
I think I
undo.
messed up.
The cos theta comes from here, which is from the double angle of sine.
Oh yeah, you're right.
So I've just factorized it out and just kept it outside.
Yeah, okay. And then that's equal.
Yeah. Yeah, and that's it. And then just hit the little left-hand side equals right-hand side. And you're done. Okay, very good. Now, second part. This one is, I would say, the more challenging part theoretically. So we want to use part A to show that cos 2 pi on 3 is a root of the equation 4x cubed minus 3x minus 1 equals 0. Again, I'll give you like 30 seconds to have a little think about it.
All right.
Yep.
So do you have to like split the 2 pi on 3 into 3 or like multiply it by 3 or something first?
Not a
Like
bad idea.
factorize out because this looks like the other equation, so
It does look like the other equation, which is the biggest observation you need to do this question. Okay, so first thing I'll ask you, what will happen if or like what's gonna look like if this is a root and I like sub it in? What's the like expression going to be over here?
it's gonna be 0.
Oh yeah, it will be 0, but more so like if I sub cos 2 pi and 3 in place of x.
Oh, it's gonna look like the other fraction.
Yeah.
Minus
So
1.
this 3 cos 2 pi 3 minus. Oh, what the hell did I just do? Oh, you go. 2 pi 3 minus 1 equals 0. So yeah, it looks oddly similar to part A. So because we can see that we have like basically this is just straight up part A, right?
Yeah.
And instead of having theta, or we
Yeah.
have theta, but our theta here is just 2 pi and 3. Why not just sub that into part A and see what we get?
Yeah.
So if we were to say let theta be 2 pi and 3, what is cos 3 theta going to become?
Cos 3 theta is cos 2 pi, which
Yep.
is just 1.
Yes, exactly.
And then so it's 4.
Yep.
Four plus
So
4 plus 1.5.
You don't need to evaluate this right hand side because so think
Oh,
the reason we're even using part A, right, is because we get this expression from just plugging it in to see that it's a root. But the thing we want to show
Oh,
is
yeah,
how we
yeah.
get this -1. And we've already shown it. We get this 1 here. So if I was to move that 1 over, then I'm just going to get this. Straight from part A, right?
S-
Because I'm just minusing 1 from both sides. And if this is the case, then 2 pi cos 2 pi on 3 must be a root of the equation because it would give you this equation here.
Wait, let me just.
Yep, take your time.
Oh, okay.
Yeah, so if I was to let this be like the polynomial px, this expression that I have arrowed here is just p cos 2 pi on 3, and that should be 0 given factor theorem.
Okay.
And then I'm just proving that using part A.
Right.
Let me know if it doesn't make sense.
No, it makes sense.
Okay. Okey-dokes. Okay, a little show question here. But I'll get Zoe to work with me for this one. So take a couple seconds to think how you're going to approach this problem.
Wait, is this for me? Sorry.
Oh, this is for Zoe.
Oh, right.
I'm not actually sure how you start this one. I was
Okay.
thinking if you
Yep.
went from the right hand side and then you assigned like that mean you'd be introducing 2 more variables. So like
Yeah.
if you made each one an angle. And then I don't know what that would help you with because then you just have like unknown plus an unknown.
Yeah.
So,
This one's start is very confusing. I will give you a hint. You want to get rid of the tan inverses. So I think how you might do that.
oh wait, is this the thing where you wait? Okay, I have a thought. If you
Mhm.
tan the right hand side,
Yep.
that means it's like tan inverse of quarter plus tan inverse of 3/5. And then your tan quarter and tan 3/5 is your A and B. And then
Yes.
you use the formula.
Yep.
So,
So I'll just
um,
write out the formula for you. So it's going to be tan A plus tan B over 1 plus tan AB. So think about what this is going to give you.
so then you would get I'm just simplifying the fraction.
Yep.
I got 1.
Yep. So I will just, yeah, 1 is correct. I'll just write out the working that you've done.
And then you tan inverse both sides. And then tan inverse of 1 is pi on 4.
Yep. Exactly. So you have basically arrived at this 3 on 5 equals 1, and then applying a tan inverse to both sides. So basically doing this and then tan inverse like that will leave you with the expression that the question wants, which is going to be the tan inverse 1 on 4, because these will kill each other, and 3 on 5 equals pi on 4, because tan inverse of 1 is pi on 4. Yeah, and just for clarity on how we got the 1 on 4 and the 3 on 5, essentially, I'll just show it for one of these. Say, for example, this was tan A. It would be tan of tan inverse 1 on 4, because that was our A in our expansion here. And from that, the tans cancel out, giving you the 1 on 4. And it's the same logic for the 3 on 5 and the 3 on 20. The 3 on 20 is just 1 on 4 times 3 on 5. So that's how, oh, actually, let me correct my formula here. This should be tan A, tan B. So that's how you get the 1 on 4 times the 3 on 5. Right, very good, Zoe. Alrighty. Some more double angle and proving questions for this next one. So for this one, Sudak, I'll get you to work with me. So take some time to have a quick look through it. Yep. But how might we start thinking about this?
Could we make the cot 2 theta e
What's the relationship between cot and tan? Think about that first.
cot is 1 over 10.
Yep. So what will cot 2 theta be in terms of tan 2 theta?
1 over 2, I mean 1 over 10 2 theta.
Yep. And are we able to find what tan 2 theta is?
Yeah.
Yep. So how are we going to do that?
We get the base angle first.
By base angle, do you mean theta?
Yeah.
Okay. So how are we going to use the base angle? Instead, I would suggest thinking about 2 theta as theta plus theta. So this is a double angle property. So if you recall, I wrote it for the previous question. I'll just write it here. But tan A plus B equals tan A plus tan B over 1 plus tan A tan B. So what will this look like if tan A and tan B are the same thing, i.e. they're both tan theta?
So tan 2 theta over 1 minus 2 tan theta. Oh wait, theta squared.
Yep. So oh yeah, this should be a minus. My bad. Just correct that. Yep. So yeah, it should be just be careful to say that it's tan theta rather than 2 theta, tan 2 theta. So it'd be this minus tan squared theta. So given that you know what tan 2 theta is in terms of tan theta, what is cot 2 theta now?
We just flip the fraction.
Yep. So what's that going to be?
So 1/10, I mean 1 minus 10 squared theta over 2 tan theta.
Yep. Perfect. Very good. And again, I'll give you some time for the second part. So we want to show that tan theta and minus cot theta are, well, by satisfying this, it basically just means we're showing that it's roots of this equation. So yeah, I'll give you some time to think of some approaches on how to do that.
What does it mean by satisfy that equation?
Basically showing that they're roots of that equation, or like roots of that polynomial.
Do we
Yeah.
do we sub and theta into the equation?
Okay, let's see what happens if we do this. So you get tan squared theta plus 2 tan theta cot 2 theta minus 1 equals 0. So where can we go from here?
Can we sub in the, like for cot 2 theta?
Mhm.
Sub in the
The expression?
yeah.
Yep. So you're gonna get 2 tan theta times
1
uh,
squared theta 1 2 tan theta.
and then the minus 1. Okay. So let's see how this simplifies. This will cancel out, this will cancel out, leaving you with tan squared theta plus 1 minus tan squared theta minus 1 dies equals 0. Yep, therefore tan theta is a root. Okay,
And then
that's one proven. Yep, and do the same thing for cot. So we get cot square theta minus 2 cot theta cot 2 theta minus 1. And then what's this going to become?
1 or 2 over tan theta and then times the fraction from before as well.
Yep. Yep. Good. We should write this as 2 over tan theta. Okay. Now, does this simplify down nicely? So what are we going to do from this point here to make it cancel?
We can cancel out the 2's.
Yep, can do that.
Or do we
What
check
about the tans?
cot squared theta to 1 over tan squared theta as well?
Yes. So if you do that, you'll get this minus 1 minus tan square theta over tan square theta minus 1, and then from this, actually does this? Yep. Oh, yep, yeah. So you'll get 1 tan square theta minus 1 tan square theta. So I'm basically just, you'll notice I'm going to be splitting this fraction into 2 parts. So minus tan square theta on tan square theta minus 1. And then evidently these will cancel out. This equals 1 because you're dividing the thing by itself. So it becomes 1 minus 1, and then that's 0.
Yep.
And therefore, it is a root / solution. There is a quicker way to do this, which is using sum and product of roots, because this is a quadratic, which is a lot nicer and it's a lot quicker. But I'll save it for sake of time. But I would recommend having a look at it in the slides later, like that I'll send out. Okay. Now on to part C. So yeah, take some time to have a look at this as well. And keep in mind that the hence means you should use the previous part. Just think about how. Okay, yeah. So any ideas?
I'm not sure what to do.
Okay, so what did we show in part B?
That tan theta and negative cot theta are roots.
Yep. And what do we have in part C? As in,
The
what are we looking at?
We have tan pi of a.
Yep. Is that pi on 8 the same as just an arbitrary theta?
Yeah.
So could we say that tan pi on 8 would satisfy the equation in part B?
Yeah.
Yeah, we can. So if we use that as a starting point, so basically from B, tan theta is a root, this is just bar for bar from the question, of x squared plus 2x cot 2 theta minus 1. So here we are letting tan theta be tan pi on 8, because that's what we're trying to find. So if you do that, you're going to get x squared plus 2x. What's my cot 2 theta going to be?
Would it still be the equation from before? The 1 minus tan squared theta over 2 tan theta?
Yes, technically, but doing that won't help us solve, because what we're trying to do is solve this, like what we're about to plug in, like this equals 0, because we're plugging in tan pi on 8 as a root, and use that to get our solution. So if you start bringing in more terms, it's going to make it harder for us. What I meant more so is, what is the 2 theta going to become?
2 times pi of 8.
Which is?
Just what is that?
Yep, so pi on 8 times 2 is?
Pi on 4.
Okay, so now we have x squared plus 2x. What is cot pi on 4 as a number? So think, what is tan pi on 4?
It's just 1.
So this just becomes 2x minus 1 equals 0. And the reason I'm writing this equals 0 is because what we proved in B. So basically we know tan pi on 8 and minus cot pi on 8 are roots of the equation.
Mm-hmm.
So this equation here. Okay, so let's solve the roots. What's my factorization going to be for this? Or can I factorize it actually?
No.
Yeah, so what am I going to use?
Quadratic formula.
Good. And that's just going to be this. So what's going to be inside here? As like the n number, do the b squared minus 4ac, and then tell me what that's going to be.
8.
Yep. Indeed it is. And can we simplify this at all?
Yeah. Is it just because it's 2 root 2 over 2,
Yep, very good, which we'll give you.
negative root 2.
Yeah, or just -1 plus
Yeah.
or minus root 2. Okay, now we have two solutions here. So which one is pi on 8 and which one is minus cot pi on 8? How can we distinguish which one is which?
Because is the positive one 10 pi on 8?
It is. Why is that the positive one?
Because 10 pi on 8 is positive.
Uh-huh. But what's like the reasoning? Because if tan is in like the fourth quadrant, actually, yeah, if tan is in the fourth quadrant, then tan pi on 8, if it was in the fourth quadrant, could be negative. So what's the reasoning for tan pi on 8 being positive? Thinking about like the unit circle. Where does pi on 8 lie within this?
In the first quadrant.
Yeah, so it's basically because tan pi on 8 is greater than 0 as it's in first quadrant. Okay, and that's why you will say, therefore, tan pi on 8 is the positive of the two, which is going to be
1 plus root 2.
and that's your answer. Very good. And last part, we want to find the value of tan pi on 16 minus cot pi on 16. And just to remember, these two roots will satisfy x squared plus 2x cot 2 theta minus 1. So I'll give you a bit of time to think about that.
So do we have to put pi on 16 in the equation again?
Yep, and do that. So, yep, if we do that, then so we'll let theta be pi on 16. So you get x squared plus 2x. What's going to be inside my cot?
So 2 pi over 8.
Good. Okay, yeah, that's the good first step. Now what to do from here? Because we can't really find a clean value for the pi on 8, can we? Yeah. So what are some other ways of solving polynomials, just generally? Because like for a quadratic, we have quadratic formula. We have cross method. What about for factorizing other polynomials? How do we usually do that? Or what are some methods of doing that? Because we're going to need to use one of them here. So one way is long division.
I'm not sure.
Okay, that's all right. So the way we're going to use here, and I will stress this as being probably the best way to solve polynomials, root coefficient relationships. So this is like your sum of roots, product of roots, etc. I think I stressed this in a previous lesson. These are like godsends for exams. So spam the fuck out of these. Okay, so we're going to use root coefficient relationships. Because this is quadratic, you only have two relationships you can even look at, which is going to be sum of roots. What the hell? Sum of roots and product of roots. But let's just look at sum of roots. So, and actually, wait a minute. Between the two, which one do you think we should look at?
Alpha times beta.
Why do you say so?
Oh wait. Oops, I meant to say alpha plus beta because we have to, because we have those roots. What?
Yeah. So I'll backtrack a bit. What are the roots to this equation? Like, just thinking straight from part B, like, what were the roots of this equation? One was tan theta and the other was?
Oh, negative cot theta.
Yep. And we've said theta is pi on 16. So our two roots are going to be tan pi on 16 and negative cot pi on 16, right? So what happens if I sum these two? Because these two are my roots. What happens if I add these two? What's it going to look like? It should look like this. So this is me doing alpha plus beta. If I let this be alpha and this root be beta.
Yeah.
Right? So this is my sum of roots. So what I'm getting from this is if I do my sum of roots over here, what I'm actually finding is tan pi on 16 minus cot pi on 16. And that's what the question is asking me for. So that's why you do sum of roots, because it basically gives you the answer to what you're trying to find in the question. Whereas
Wait.
if you do,
Let me say that again with the tan and cot thing.
Yeah. So from this equation, your two roots are going to be tan pi on 16 and minus cot pi on 16, which is what we proved in part B. So if you're to add these two together, letting tan pi on 16 be alpha and minus cot pi on 16 be beta, just generally naming our roots, you're going to get tan pi on 16 plus minus cot pi on 16, which just gives you tan pi on 16 minus cot pi on 16. And that's what the question is asking you for. What is the value of tan pi on 16 minus cot pi on 16?
Oh, okay.
So, yeah. So by choosing to do sum of roots, whatever you get as your answer will be the value of tan pi on 16 minus cot pi on 16.
Okay.
So that's why we choose to do this. So this is going to be, so this is your left-hand side. So this is just what adding your roots will give you, which is this, as we've discussed. Okay. And what is this going to be in terms of like my coefficients here, like your A, B, C's here?
Negative b on a.
Yep, negative B on A. And what is B and what is A here?
2 and
Therefore,
oh,
just before you move on, is it just 2? Remember, this is a polynomial in terms of X.
2 cot pi on a.
Good. And A?
Just 1.
Yes. So it's just going to be 2 cot pi on it. Okay. And if you recall, from part C, we found tan pi on 8, right? Give you a moment to have a look. So we found tan pi on 8, which meant the other root was going to be minus cot pi on 8. Because there was two roots and we just found one of them, right?
Yeah.
So what we can say, I'll put it in red. from C, we know that minus cot pi on 8 will be the other of the two answers. So it'd be the -1 minus √2 case.
Yeah.
So therefore we can say 2 cot pi on 8 should be actually, one second. Actually, is this a 2? Yeah, it should be. So then, yeah, what we can say is that this is going to be 1. Actually, should this be negative? Hold on a second. Yes, it should be. Interesting. Oh, right, that's why. There should be a negative sign here. That's my bad. So I was just confused here. Okay, yeah. So because it's times 2, what we can say is it's going to be -2 minus √2 like so. Or 2 √2 rather. So this is what 2 cot pi on 8 is, given we know this from part C.
Yeah.
So since we know that, we can therefore say that tan pi on 16 minus cot pi on 16, just bringing these down from up here, will equal to -2 minus 2 √2. And that's your exact answer.
Okay.
Yeah. That one is a long and pretty difficult question, so don't stress too much. Okay, so we'll do some differentiation now. Just before we do, I'm not going to run through them in much detail, but I'll just put the inverse trig calculus stuff here for you to refer to. So hopefully you know it by now, but if not, feel free to use this as you're doing the questions. So essentially, you don't need to remember cos for either of these. Just remember sine and tan. So diff of sine inverse of x is going to give you f dash x from chain rule, and then 1 minus f of x squared. Okay, and on the other hand, diff of tan inverse gives you the f dash of x from chain rule over 1 plus f of x squared. So you can read those from there. So I'll just write a more simplified form, but basically it's just going to look like this. Similar to this, whereas this will look like so. And then for the integrals, so if you're looking at something like this, x squared, this will become sine inverse x on a. And similarly, if you're looking at something like so, this will be tan inverse x on a. So this is, they don't tell you this in the like formulas here that I've pasted in, but it's very important that you know the a version of the integral, because they virtually always will have the x on a thing. So keep it in mind. Okay, that being said, we'll do an inverse trig differential question now. So for this one, I'll get Shruti to work with me. And I'll give you like 30 seconds to process the question. Okay. So, what are your ideas so far, Shruti?
Would you use product rule?
Yep, indeed you would.
So first you'd have the x,
Mhm.
and then you differentiate tan inverse root x.
Sure. Yep, that works.
So
What would
Um,
the diff of tan inverse root x look like? You can also use the screen clipping above, which shows the differentiation.
so you differentiate root x first.
Mhm.
So that'd be 1 on 2 root x.
1 on 2 root x. Good.
And then over 1 plus root x squared. I mean, first root 1. Oh, wait, never mind, there's no root.
But there is a root.
Yeah, okay.
Oh, like an overarching root.
Yeah.
Yeah. So, what are you saying the second part of this would be?
It'd be 1 plus root x squared.
Uh-huh. And what is the root x squared going to become?
X.
Yep. I'll write that in the next step, but yeah, just to think ahead. Okay, and are we done with this line?
And then plus.
Yep. Plus what?
And then you'd have it'd just be tan inverse root x.
Good catch. Okay, so I'll do the simplification really quickly. So yeah, you get down to this line. Can we simplify this any further?
You could put the 1 on 2 root x times 1 on 1 plus x squared together. So just
Yep, you could combine these. Also, just going back for 1 second, did we miss something in this line, particularly in this first half?
the x.
Yes, the x. So don't forget to write that as well. I always recommend, like, when you're doing the product rule, write your non-diffed term first immediately, just so you don't forget.
Okay.
But yep, so this should instead be the x over here. And yeah, you just combine it from here. There's not really much else simplification you can do.
Yeah.
Like so. All right, nice. Okay, this one's going to be a slightly lengthier differentiation question. So, let's see. Zoe, I'll get you to have a look at this one.
So I would do the differentiation first and then substitute it. So for the first one is product rule. So
Yep.
it would be sine inverse x over 4 and then times 1 plus x over root 1 minus x squared over 16.
Oh, sorry, repeat that again.
X over
Yep.
root 1 minus x squared over 16.
X over root. Yeah. um, I would write it like so, but yeah, same thing.
And then the next part is just you can use chain rule. So then you get x over 2 root 16 minus x squared.
Yep. X over 2. Hold on a second. So you said x over 2 and then what, sorry?
And then on the bottom of the fraction is the root again.
Yep.
16 minus. Yeah.
Okay. Very good. One correction. Should this just be x?
Oh, I think so. Oh, the negative. I missed the negative.
There's one more thing as well. Think about what you're chain ruling on the inside. See, negative x squared, right?
Yep.
So what is diff of x squared? Just space x squared.
But isn't it because it's a power that it's half? Oh wait, no, yeah, understand.
Yeah,
Okay.
like the chain rule on
Okay,
the
yeah.
inside. Yep.
Yeah, the 2's cancel out. Okay.
Yeah, the 2's cancel out. Yes, exactly. Yep. So the 2's cancel out. And because the 2's cancel out, what else cancels out?
The 2 fractions.
Yep. So this gives you sine inverse x on 4.
Mhm.
Right.
And then it
And
just be
Mhm.
sine inverse half, which is pi on 6.
sine inverse 2 on 4. Yeah. Very good. Just like a quick side note on this thing here, because I think like what you said was correct. I think you said the way which was like something like this, right? I think you mentioned it like this way from memory.
Yeah.
Yeah. So this if I remove the x, this is basically the same as if I was to write it like so. So that was if you remember, just going up, the way I mentioned with like using the a's, so up here, that's basically what that is. So I've just rearranged it into, instead of having x on 4, I just transport that 4 over here as a 16. So
Mhm.
just making that the 4 squared. It just makes it look nicer, I find, and it also is just easier to calculate.
Okay. Thanks.
Yeah, no worries. Okay, next. Let's see. Okay. Another differentiation question. And this one, Jonah, I'll get you to help me out with this. So yeah, again, take like 30 seconds. Okay, so what are your thoughts for part A? Fun?
Do you, is it just negative infinity to infinity?
Close. So when we do sums of graphs like this, we're basically adding
Uh-huh.
two graphs, right? The domain will be the intersection of both domains. So it'd be like the subset of
Oh,
the
right.
domain of
Okay.
tan inverse x and the domain of tan inverse 1 on x. So what's the domain of tan inverse x?
Negative infinity to infinity.
Yep, I'll just put it as all real. So,
So yeah.
yep. Okay, what about tan inverse 1 on x?
Uh,
Think in particular about the 1 on x. What are the limitations of that?
it can't be 0. So
So,
it's infinity, negative infinity to 0, 0 to infinity.
yeah, so just write it as all real except x can't be 0.
Okay.
And since it's the intersection of the domains, domain of the whole graph will be basically the smallest grouping of these two domains, which is just going to be the domain of the tan inverse x, or tan inverse
Right.
1 on x.
Okay.
Like so. Okay. Second part, we want to show that gx is constant over its domain. How do we show that something is constant?
Sub in. So do we differentiate?
What would differentiating achieve?
You get the root.
You will
No.
get. So think like generally, what does differentiation actually give you in terms of a graph?
The I don't know. I forgot.
Oh, good. So I'll draw as like a little diagram. So if I was to diff at like this point here, what I'm finding is the gradient.
Right. Yeah.
Right? So if something is constant, i.e., it will look like this, what is its gradient?
0.
Yep. So what we're trying to prove here is that if we differentiate it, its gradient or its differentiation is always going to be 0.
Right.
So basically what we're trying to do is show that if we take g dash of x, it's always going to be 0. So let's start with taking g dash of x. So what is that going
So
to look like?
that's 1 on 1 plus x squared
Yep.
plus x to the minus 1 on 1 plus 1 on x squared. And then
You're
that could
very
be
close. Just to backtrack a little. Think what this should be.
oh
General.
no, x to the minus 2
Yep. It should be minus x to the minus 2.
minus it, right? Okay.
Yep. Okay. Yep, this is correct. So let's continue from here.
And then you can take the x down.
Yep. Indeed, you can. So x down here. Sure. And what about, can we just expand this in one step?
Yeah, then it just becomes 0. Oh wait, I already
Yeah,
yeah, it
yeah.
just becomes x squared plus 1.
Yep. Oh yeah, sure, this should be x squared. Plus
And then
1.
that's just 0. So it's a constant.
Yep. Okay, this is correct. And for most questions, this is enough, but there's one last thing that it's not like required for this question, but it will be for others. You need to show or state that it has no discontinuities. So what I mean by that, or you need to, actually no, for this question, it's fine. But what can happen is you can have a graph, and I'll run through a question like this after this one, where it'll go like this, and it'll be constant, and you have a discontinuity, and then it's no longer going to be constant. Like
Yeah.
so. So a good habit would be to like say, hold on. Because we know we have a discontinuity at 0, right? Because of the tan 1 on x, tan inverse 1 on x rather.
Mhm.
What you should do as general practice is, so our f of x is tan inverse x plus tan inverse 1 on x. You should sub in a point on the left side of the discontinuity and the right side of the discontinuity and show that it's still equal. So what's a number less than 0? Just a random number.
-3.
Sure. I would have hoped you said 1, but I'm gonna choose 1 because it's nicer. But
Sure.
you can indeed do -3 if you want to. Okay, so this is going to give you this, and then if you were to plug that in, you get tan inverse -1. You'll get -90. And then if you plug in f of 1, so the other side of the discontinuity, again, this doesn't have to just be 1. It could be like 67 for all I care. Why did I say that number? And then if you do this, tan inverse, I mean, this is going to be 90 because each of these are 45. So, actually, hold on a second. Actually, yeah, this GX actually isn't constant over its domain, funnily enough. Yeah, that's interesting.
Yeah, I don't think it is.
Yeah, it isn't. It isn't. Because this is -90. Okay, yeah. So actually that question's flawed.
I feel like I did like some of the HSC practice from the AutoSmart thing, and like a lot of the questions had like little things that made them sort of undoable, and even like the answers were like kind of bad. So
yeah, that is indeed the case. Because
yeah.
So this question is actually like incorrect. It's not. So a correct way for this question to be asked would be like if GX is constant over like x between like 1 and infinity or something. But actually, yeah. So from what you can see here, it's actually not constant over its whole domain. Okay. In any case, side note over, we'll do part C, which is to sketch the graph. And what we've actually just done gives us everything we need to know to actually sketch it. So what might it look like, Jonah?
Oh, well, there's gonna be
I think where's our discontinuity going to be? To
I
start.
mean, in at x equals 0.
Yep. And then after that point, so if we're looking for positive values of x, what's my y value going to be?
At 0.
No, so as in like from here onwards, what
Mhm.
is my y value going to be? Remember, it's constant after the discontinuity.
Oh,
So we've
pi
checked it here.
pi on 2.
Yeah, pi on 2. So that's just from this 90 being pi on 2.
Right.
Okay, and should this be a closed or open circle here?
Open circle.
Good. Okay, and what about on the left? What's that?
Negative pi on 2.
Very good.
Is that actually
Yeah, what were you asking?
Is that right?
Yes, that is right.
Because I just put it into Desmos and it's like giving me a completely different thing.
This should be correct. I can Desmos it real quick as well, just to check.
I'm getting like a. Yeah, you just do it.
Because this is a pretty common question from memory. Let me see. Right, is it not? Hold on a second. Okay.
No, it is right.
Okay, yeah. It should be, yeah, this should be correct.
Yeah, okay, that's my bad.
Oh, good. Okay, yeah, that's the end of that question.
All right.
Yeah, does that make sense? The
Yeah, it
discontinuity thing?
makes sense.
Cool. Alright, let me find the other discontinuity one. Oh, actually, I think that might be the. Oh, wait, no. Yeah, here it is. Okay. Yeah, so this. Oh, wait, no. This is an extension of that. Okay, so yeah, that is the only discontinuity question. My bad. In that case, we'll do an auxiliary angle question next. Okay. So for this one, I'll get Shruti to work with me. Have a read through while I'm pasting this in. Okay. What are your thoughts so far?
I'm actually, I don't remember, but I know you expand it. I think you expand the r sine theta plus alpha.
Sure. So what is this expansion going to look like?
So it'd be r and then r sine theta cos alpha.
Yep.
Plus r cos theta sine alpha.
Yep. And what is this going to be equated to?
Cos theta minus √3 sine theta.
Yep. So like so. Okay. And where do we go from here?
And then you make r sine theta. That equals to, I'm not sure if it's minus √3 or 1.
So I'm going to backtrack you for a quick second.
Yeah.
So what we want to do from this line is basically equate coefficients. So on the right side, we have cos theta, whose coefficient is just going to be 1. And on the left side, we have this cos theta here. And the coefficient around that is going to be r sine alpha. So what we can say is basically this. R
Sine alpha equals 1.
Yep. Because they have the same variable, call it, which is cos theta. So
Mhm.
what about r cos alpha? What's that going to be equal to?
Minus √3.
Yes, exactly. So now we have this. How can we find r?
Square them.
So square them individually, or do we do anything with them?
So it'd be r squared and then sine squared plus cos squared, which just equals 1.
Right. So like this. Yep.
And then squaring 1 squared and minus √3 squared. So that'd be 4.
Yep.
So then r would be 2
Why not -2?
because it has to be positive. Because
Yep.
r is, yeah, positive.
Yep. Just don't forget to write them.
Okay.
Okay. And what is alpha now?
You do sine over cos.
Yep.
So tan alpha equals, and then 1 over minus √3.
And therefore alpha is?
√6 minus √6.
Okay. So be careful of your domain. It's between 0 and pi. So,
So it'd be √6.
but can it though? Because we have tan alpha equals -1/√3. So this is where you need to be careful about like just putting like a tan inverse on your calculator. So
Mhm.
here's where you would need to consider like the unit circle thing. So from our quadrants here, we know that we can't be looking at T and C because we're only looking between 0 and pi.
Yeah.
And we know that this is a negative sign, so it can't be in the first quadrant. So it can only be somewhere in this second quadrant here.
Oh, so we do pi minus √6.
Yes, exactly. And that is?
5 √6.
Exactly. Very good. And so what is our final expression?
It'd be cos theta minus √3 sine theta equals 2 sine theta plus √6.
Pi and 6 or?
I mean 5 √6.
Yeah. Good. That would be an answer. Nice. Okay. And second part of the question, I'll give you some time to think. So hence, i.e. using part A, solve cos theta minus √3 sine theta equals 1 for theta belonging to 0 and 2 pi. So take a moment to think about how you're going to approach this question.
So you'd use the answer from the previous and make it equal 1.
Yep. So that was 2 sine theta plus 5 pi on 6. And then letting that equal 1. Sure.
And then you can move the 2 and make it sine theta plus 5 pi on 6 equals half.
Indeed you can. And what from here?
I'm not sure.
So from here, what I would recommend doing, first of all, we need to remove this sign, which means we need to move it over there. But before we do that, we're looking at theta plus 5 pi on 6. This changes our domain. So now, instead of being from 0 to 2 pi, we're looking at this.
Oh,
2 pi, so 2 plus 5 on 6 to 17 pi on 6. I don't think it will impact the answer on this question, but it's a common trick you'll see in HSC question. So whenever you have like a different thing, like not theta in the sign here, or like whatever trig function, always make sure to rewrite your domain, because if you don't, you're going to leave out solutions that you should get. But in any case, what we should do from here is basically move the sign over and see what we're going to get for our values of theta plus 5 pi on 6. So which quadrants are we going to be looking at? Given that this is positive here.
So the first two.
Yep, exactly. So let's do that. So the first one should be, what's our first quadrant answer going to be?
5 pi on 6.
That will be your second quadrant answer, I believe. Because how'd you get the 5 pi on 6? Did you do 180 or like
No, I
pi
just
minus-
literally took it from there.
Oh, okay, yeah. Okay, so what I've done is just to get the first quadrant answer, I just took sine inverse of positive a half.
Right.
And that gives you pi on 6 or 30 degrees. And then the second quadrant answer is going to be pi
Pi
minus pi on 6. Yep. So 5 pi on 6. And now I want you to think, is there going to be another answer that is in this expanded domain?
Yeah.
Okay, how can we find it?
Add 2 pi.
Yep. Which one are you going to add 2 pi to?
The pi on 6.
Sure. And what does that give you?
13 pi on 6.
Good. And we should also, for good practice, just check the 5 pi on 6. So
Yep,
what does that
that's
give?
17 pi on 6. So in work as well.
Indeed. So we can also get 17 pi on 6. Okay. And now what are we going to get for theta?
And then you minus the 5 pi on 6.
Yep.
with all of them.
Indeed you do. And just backtracking for a quick second, can pi on 6 be an answer?
No.
Because of our domain, but these ones all can be.
Mm.
Okay, so what will our answers for theta be?
So 0.
Mhm.
And 4 pi on 3.
Yep.
And then 2 pi.
Yep, exactly. And that's our final answer. Okay. That brings us basically to 8 o'clock. Does anyone have any questions for Q&A? From like previous weeks or homework, anything?
Did we actually go through 12 from this lesson?
Well, sure. Did we go through it in the questions, or have I not gone through it?
No.
I have not gone through it yet. Okay, let's have a look. Yeah, okay. Yeah, this is gonna take me a little second. I've not solved this question yet. Okay, I'll just paste it in here. Is it like part A continued or like a specific part?
Just all of it, I guess. I have no idea where to start.
Okay, yeah, sure. let me see. A is a real number, a belongs 0 to pi, and is an integer. Pn is a series up to that, so sure. Okay. Show that Pn sine alpha on 2n equals half Pn minus 1. Okay. Right, so I'm gonna, okay, when I'm looking at this, I'm thinking, I don't know what the hell's going on with the right-hand side, but I can see the left-hand side looks something alike to what's given in the question. So I'm gonna start with that. This is my live, like, thinking process, by the way, so I'm just gonna explain as I go. So this is going to be cos alpha on 2, it's just multiplying a sine alpha on 2n to both sides. Alpha. And then cos alpha on 2n, and then it should just be a sine alpha on 2n as well. Okay, so then that's that. And now I want to make it look like that. Okay. Right. Okay, from this Pn minus 1 is just going up to the last term. So cos alpha on 4. And then it's just going up to this. So I need to essentially source a half sine alpha on 2n minus 1 here. And that's going to basically be the equivalent of this thing here, from what they're trying to tell me. So I need to somehow make cos alpha on 2n times sine alpha on 2n. Here. On 2n look like a half sine alpha on 2n minus 1. Can I do that? Yes, I can. So this looks like a sine double angle. So this looks like a half outside of 2 sine 2 alpha on 2 to the n, which is going to be sine. Actually, but what? Actually, no, wait, what am I doing? It should be like this, because then this is half times 2. Okay, yeah. So I'm basically just forcing this to look like a sine double angle from here. And from this, you get alpha on top, and then this is going to become 2n minus 1. So I'm just absorbing this 2 down here. So then we've basically shown now that this red section here is equivalent. So I can rewrite this as alpha on 2 cos alpha on 4, yada yada yada, cos alpha 2n minus 1, and I can put a half here and say that this is sine alpha on 2n minus 1, which is equal to a half Pn minus 1 sine alpha on 2n minus 1. Does the logic make sense?
Kind of.
You can tell me if it's
Um,
confusing. Because yeah, I was just like speaking as a go. I can explain it retroactively. So my thought process as I did this question is one, spam the hell out of what they've given me, which is this. So from the left-hand side, I decided the left-hand side looked more straightforward to me than the right-hand side, which is why I started with that. Because all it is just what they've given you times by a sine alpha on 2n. So that's what I did in this first line here. Yeah, I'll write it in a different pen color. So that's what I did in the first line here, was just basically times the sine in. Then I looked at the right-hand side and what that actually looks like. So firstly, I was like writing out what Pn minus 1 looks like. So if Pn up here goes to the nth term, Pn minus 1 just stops here. So that's what I just wrote down. It'll just go up to the n minus 1th term. And then what I've realized is what I'm basically trying to prove, or rather, let me backtrack. So if you look at Pn sine alpha on 2n, so the left-hand side, and you compare it to what Pn minus 1 looks like, everything is the same up to this cos alpha on 2n minus 1. Where it differs, actually, let me write this in here as well. So where it differs is I have this extra term here from my right-hand side, like the half and then the sine alpha on 2n minus 1. And on the left-hand side, I have this extra cos alpha on 2n, sine alpha on 2n. But before that, so everything from cos alpha on 2, cos alpha on 4, all the way up to cos alpha on 2n minus 1 is the same between both of my sides. So the only difference from the left-hand side is the cos alpha on 2n, sine alpha on 2n. And the only difference on the right-hand side is this a half sine alpha on 2n minus 1. So what you're essentially trying to do in this question is show that these two things are equal, because everything else is the same. You just want to show that the two things that look different are actually equal. Therefore, the whole thing is the same. So my approach of doing that was to recognize that this looks like essentially a sine double angle. So like sine alpha on 2n times 2, because that would be 2 sine alpha on 2n cos alpha on 2n. So just the general like sine 2 theta expansion. Except I don't have a times 2 at the front, so I just took a half sine 2 alpha on 2n instead to get rid of this 2. Okay, and then within here, I have 2 on 2n times alpha. So I can just absorb this 2 down here as a 1 on 2n minus 1 times alpha. Does that make sense? Okay, yep. And so then that leaves me with a half sine alpha on 2n minus 1 from this. And that's the same as my right-hand side. So I've basically proved the two things that look different are the same. Therefore, the whole thing is the same. Yeah?
Yeah, that makes sense. Thank you.
No worries. Did you want to go through the rest of the question, like, and have a go yourself first, or do you want to go through it now?
Could we go through it? Because I'm not sure how to do it.
Yeah, sure. put me on the spot. Okay, let's see.
Because I initially tried rearranging like the thing they gave us and then using n equals 1. So then n
Yeah.
minus 1 would be 0. But then I don't know what p1 is.
Yeah. Okay. So prove that p
And this
zero.
isn't a series, right? Because there's no like pluses, so we can't use limiting sum or anything.
Yeah, no, you can't. Okay, so if we try just subbing it directly into what they've given us, that is yeah, you can't do that because yeah, you can't do that because your first term is F1, 2. That doesn't make sense. Okay, sure. I'm gonna try use what I showed in part A because I can't sub it directly in like to what they've given us, like as you've noticed as well. So I'm gonna just this is like the point where you just like throw ideas until one works. So I'm just gonna okay, I have an n minus 1, so I'll let that be 0. So p sine alpha on 2 equals a half p0 sine alpha on 2 to 0. So p1 sine alpha on 2 equals a half p0 sine alpha. Okay. Is that true? Okay. Just get p0 by itself. No. Okay. Right. Okay. What I can say, I know I can find P1 from what they've given me. So I know from the expression they gave in the question that P1 can equal to cos alpha on 2. Yep. So my left-hand side can then become cos alpha on 2 sine alpha on 2 equals a half p0 sine alpha. Okay. And then I'm just going to remove the half just because I don't like seeing it. So I'm going to say 2 cos alpha on 2 sine alpha on 2 equals p0 sine alpha. So, oh wait, yeah, that works out. Yeah, so now from here, this is sine alpha. Because this is the equivalent of me writing it like this. Alpha on 2 plus alpha on 2.
Where did you get the p1 equals cos alpha over 2 from?
Yeah, so that comes from up here, like from the original Pn expression. If you take n to be 1, because this is basically your first term will be where I got that from.
Oh yeah, of course, it's like induction.
Yep. So that's where I got it from. It's from the first term. And that's why I say from given. So it's from the given expression in the question. Yeah, and then so you can say you have sine alpha equals p0 sine alpha, and therefore you can say p0 equals 1 because it's just sine alpha divided by sine alpha.
Okay, thank you.
No worries.
I think the next one is easy, it's just rearranging.
Yeah, looks like it.
But I wouldn't know how to do the last one.
The last one?
Yeah.
Given that x is greater than sine x for x greater than 0. What the hell? Okay. So that looks like well, I'm just got teleported. Okay, so that looks like
The bottom would be
sine alpha.
Pn,
Yeah.
but then I
this
don't know what you do from there.
I'm trying to prove this. So you're trying to prove sine alpha is alpha Pn. Hmm. Okay. Think. Trying to see if I can use the previous parts. Okay. Think. What the? Okay. I feel like they haven't given this for no reason, considering I have a sine alpha and I have an alpha. So in fact, I think this is a better starting line. So I just do like backwards reasoning. So from this, what can I say? Sine alpha and Pn. Have I found an expression for this? Oh wait, no. From the previous part, like from part C, assuming we've proven it, I can say that sine alpha on Pn equals 2n sine alpha on 2n, right? So I can re-express this as 2n sine alpha on 2n is less than alpha. This is from C. Okay. And then what from here? Okay, I can wait, actually no, that's perfect. Sine alpha on 2n is less than alpha on 2n. And then this just brings me back to this. Yep, okay, got it. So, to explain what I did.
It makes sense, but then when you're proving it, do you have to go the other way?
Yeah, you just have to write it the other way. So
Oh, okay.
this is backwards reasoning. They don't accept backwards reasoning. So basically you just write it this way as you're solving it. Ideally on a separate piece of paper. And then on your actual exam booklet, just write, oh
The
yeah,
other
so
way.
I'm starting from sine x less than x, because I know what I'm doing.
Okay.
But yeah, I would do this using backwards reasoning, because otherwise it's like, this is a very hard thought process jump.
Yeah.
Yeah.
Okay. Thank you.
No worries. But yeah, just make sure you write it in the reverse order when you're actually writing in your exam booklet. Okay. Does anyone else have any questions? Could be about any homework from past weeks or anything from today's lesson. Okay. Because if not, I'm just going to do another question.
I've just got a question about the content.
Yep.
When are we gonna do slope fields?
I don't think slope fields is. I think we
Is
have. I think we have touched on it on memory.
Oh, I might not have been here. If it was like, I think last lesson I wasn't here, so if it was last lesson.
I think it might have been with.
Oh crap. Okay.
I sent everyone a PowerPoint copy of the slides in any case.
Oh yeah, I'll just watch the YouTube. But that's like the thing I have no idea about. And then are we doing like stats next week?
Next week is like yeah, series, data, and finance. So like
Okay,
finance.
right. Yeah. Okay,
Um,
that was my question.
yeah, all good. I mean, I can just go generally over the theory of slope fields. What part like confuses you, or like are you just like not really?
I just like wasn't in class when we did them, and I never really took the time to learn them.
Okay, yeah. Okay, I can just give you a quick crash course right now.
Thanks.
Let me just pull up an image of a slope field because I don't trust myself to draw one. Let's see. But what a slope field is just it's a bunch of dashes, and they essentially just indicate your slope at that point. Hence why it's called a slope field. So, let's do it down here. So what it means, if you have a look at the bottom, is if I'm, say, looking at like this dash right here,
Mm-hmm.
what it's saying is at that point, my gradient will directly align with this. So what you can do, so there's two types of slope field questions. Basically, one is, okay, let me clarify. So you'll only really see slope fields in multi-choice for 3U from everything I've encountered. And usually what they'll ask you is, here's a slope field, which function is it? A, B, C, D, E, A, B, C, D. And you just need to identify which one it is. And generally, they'll have things that help you tell. So like, okay, this one isn't a great example, but there was like a one, I'm pretty sure it was asked in a previous lesson, where it had like a constant gradient like across like this for like all of them, which meant that like things didn't have x dependence. Okay, I'm getting ahead of myself. Basically, everything here represents a slope. So if I pick a starting point, say here, and I was to draw a curve, it would have to follow every one of these gradient points. So if I was to start, say here, I'd start here, go here, go here, go here, and you can see that these gradients along this line are all constant. So I'm just gonna follow a straight line. Alternatively, if I was to go like here, this would flatten out, this increases, and then this goes up like so. Or if I was to pick, for example,
But isn't it like the the differential equation?
yes, it is. So like when they give you examples for these questions, it'll be like y equals like x squared plus x. And what you will need to do to check which one it is, you actually have to diff it. So you'll need to go like equals 2x plus 1.
So what
Let me actually see if I can find a slope field multi-choice question. That would be, oh wait, no, I think I remember it was from, I remember it was
if you
from,
could draw like if yeah, that'd be good.
I'll pull up a question. It was from the mock exam. That's where I remember it from. Let's see. I think I remember the exact question. Yeah, here it is. So it'll be in all of my time doing math, they've only ever asked it in short answers for 3 unit. It'll basically be a question like this. And let's see. So from here, it gives you like some differential equations. So these are the derivatives. And you have to work from this. So like with a question like this one, you can see that at every gradient, hold on, what is it? So all of the gradients, if you're looking like down the x-axis, they're all the same. So these dashes all have the same slope. These dashes all have the same slope. So what that tells you is there's no x dependence. So there's no x in the derivative. So it can't be c or d. So then you're determining between a and b, which is the slope going to be like y on 2? Is it going to be negative y on 2? So for that, you look at a specific point. So let's take, for example, y equals 2. So if I plug, or if I look here, this slope is negative, right? So whichever one it is, it should give me a negative slope. So if I look at a, I get dy dx equals negative, I can erase, negative 2 on 2 at the point where y equals 2, like here, which gives me a slope of negative 1, which checks out. If I look at b, I get, so y on 2, so just 2 on 2, which is positive 1, which doesn't check out because, as you can see here, my slopes are negative, not positive. Does that make sense?
Yeah, but if you could like draw a line just to demonstrate like what
How to follow it?
the yes, or like could you draw like one variation of the diff
Sure. So if I was to, for example, start here.
graph, I guess?
Yeah, so if I start here, I'm following this gradient up until I get to this point. Then I follow this slope. And I continue. Basically, at every point where you see a dash, you adjust your slope to follow that dash exactly.
Yeah, but if
So
it keeps going like
yeah, if it keeps going.
can you see my thing?
I
If
can,
I
oh,
if I like
kind of.
draw it, can you see that? Oh,
Yeah, yeah.
hold on. Oh,
Yeah, I can see it.
that's not what I. Wait, what like thing are you using?
I'm just using the pen tool.
Oh yeah. So we'll go like here.
Is your one the red line?
And then what? It would go like here.
Let's see. Yeah, this one's a bit of a goofy one. Because yeah, it would go like so. Yeah, I think this one would asymptote.
Because
so.
like if it was a single graph,
What do you mean by if it was a single graph?
yeah, but why is there like why is there another side to it? Like
Because there's multiple curves.
like
Basically, it's not a
because you know
single
how
slope. So like all of these are equally
no, I
like
know,
correct
but
paths, like so.
oh,
Like this. So it's not just like one graph, but like what questions can ask you to do is like graph a single one, like a single line. And then they'll usually specify like a single solution to the slope field that
I
goes
wouldn't
through, for
know
example,
how
y
to
equals 2.
because
Pardon?
like do you have to get
Do you have to get what, sir? I think your mic is cutting out. Wait, what did you say?
every single part of it? So like go to the one at the top, like the one above. Can
Yep.
you not hear me?
Oh, yeah, I can hear you now.
Let me just switch my mic. Hold on.
No, it's all good. I can hear you now.
You can hear me now?
Yep.
Okay.
They're just lighting up.
Um, yeah, if you're gonna draw
Oh, it cut out again. If I was going to draw, I'm gonna try and interpret your question because I can't hear you right now. But are you like, I'm assuming you're asking
the line
like,
on the top one, how like
Oh wait, can you just ask your question in the chat?
It's cutting out.
Yeah. Like if you were to like draw a line up here, it would just look like this. And then it will branch off. I'll just draw a bunch of example ones for you. Basically should look like this.
And so those are all correct.
Yep. Those are all like, yeah, those are all the slopes. But what it can ask you is like, draw the slope or draw the curve in the slope field that goes through the point 2. And then to do that, you just like backtrack from here. And it should look like this, like the one in purple.
Okay.
Yeah.
Yeah, I was just kind of confused because like when we didn't have slope field, like last year when we were doing, or not last year, but maybe earlier in the year,
Mhm.
when we were doing differential equations, like graphing them,
Mhm.
and it would just say like draw one variation of this, because like that if you had like a
Yeah,
like
that's the thing. There's like infinite variation.
yeah, but I thought it would only like for example, if I'm just gonna draw an axis to the
Yeah.
right, and like if the thing looked like this, then there'd be like this.
Yeah.
this. Do you see my thing?
Yeah, I
My
do.
Are you talking about like family of curves though? So that's like the plus
yeah,
C
yeah,
from
yeah,
integration.
yeah.
Yeah. So I think family of curves is different to your differential slope field.
Oh, it is.
Yeah, I believe so.
Because family of curves comes from the plus C from integration, and then your slope field comes from your differential equation.
Yeah, you're right. Okay. Yeah, that was what I was confused about.
Yeah. Thank you, Zoe.
Thanks.
Okay, yeah. All right, that's gonna be all for the lesson. If you guys can, please try go through the mock exam too. I've made sure it is actually up there this time. And we'll like spend some time next week also reviewing that because it's also our last lesson. Okay, thank you guys and enjoy the
Thanks.
rest of your week.
Thank you.
Thank you.
See ya.